multiplexes or sub-wavelength structures, for which you cannot use things like Zemax, ray optics, or even diffraction theory, or things like beam propagation methods. You have to use things like COMSOL or finite time difference time domain, more heavy methods, which take a long time and but are very accurate and very powerful. So what we hope to do with neural networks or learning techniques is get speed for sure, increase the speed, and while not giving up too much of the accuracy or none of the accuracy. And it's particularly important for inverse scattering problems, where often you have to iteratively calculate the fields produced by different candidate dielectric or optical configurations. Let me see. Not sure why they are here. Okay, so the idea is to have a network, deep neural network, where you give it the dielectric constant as a function of three-dimensional position, and the network is trained. Its weights are adjusted to produce at the output a three-dimensional electric field that's consistent with the illumination, the boundary conditions, and the propagation through the electric constant. So one way to do this would be to have many different examples of inputs and outputs, and use these examples like in conventional way to train the network. But the problem with that is speed again, because you will have, particularly for three-dimensional structures, you normally don't have ground truth. It's very hard to know the three-dimensional field inside the three-dimensional structure. So you will have to use numerics calculations again, which would be something like COMSOL. So it would take a long time to produce a training set. And also it's not clear how that would generalize. So what we would hope to get is a network that is much faster to read out and generalize without the need for having a ground truth. In other words, just having the dielectric constant of the material, like a lens or a grating or whatever else the optical system is, presented as an input in 3 dimensions to the network, and have the network produce the representation, the answer of the 3-dimensional distribution of the field. So that's the goal. And to do this without examples again, but to do it just the constraints that since it's the field has to satisfy Maxwell's equations, that becomes the loss function. Any deviation from satisfying the Maxwell's equations is an error function which is used to modify the weights and make the network do the right thing. Okay, I'm not going to go through Maxwell's equations for you. I'm sure that you've seen them, or you haven't seen them, you're not going to learn them today. But just to point out that the system we're going to be using is something without charges, no charge density, no current density, and we're going to mu is going to be constant. So you just have the electric permittivity or index of refraction equivalently that's varying as a function of 3-dimensional space. And then under those conditions, under steady state or in the frequency domain, Maxwell's equations reduced to the well-known wave equation. So this then would be our loss function. In other words, we'll be putting in an epsilon distribution as a function of position, and we will be looking for a field. We'll be looking for a network that will produce a field E that's consistent with this equation. If the equation is not satisfied, we'll have an error, and then we need to change the weights, just like conventional training. Okay, just to see what this error signal looks like. Again, up on top is this wave equation again. What you see on this side, I hope you see my cursor, but do you?
Yes, we can see it.
Yeah, perfect. So the index distribution that's modeled here is a spherical lens, something that looks like this shape here. So on the top, we calculated the field E using the Born approximation, which makes the problem easy. In other words, you assume that the plane wave coming in along Z from the left. These are all two-dimensional simulations. I'll talk about this a little bit later on. And the plane wave arriving from the left, as it propagates through the medium, remains a plane wave throughout. In other words, any reflections or refraction or other effects due to the lens are not affecting the incident wave. We have a scattered field because of the dielectric constant, and then that modifies that gives you some approximation under the Born approximation of what the field is. But the thing is not accurate enough. So when you plug into this equation, this part of the equation, obtain this value, this quantity as a function of x and z. When you take this part of the equation and you plot it, you get this. The difference here is this. So this is an error. Run COMSOL instead is a much more accurate method. The field is much more complicated, primarily because of the reflections and interference because of that. And then this is what the field looks. This is what the two terms look like, which is proportional to the field, at least on this side. And the residual or the error is very small, just at the edges because of the inaccuracies because of quantization errors. So what we're going to do now is take this residual field, this error, whatever it is, have a network produce some current estimate of the field given the dielectric index distribution, take that field, substitute it into the wave equation. If there's an error, then use that error to change the weights of the neural network to try to do better. The network that we use, we have not really tried to optimize the structure of the network or the architecture of the network to best fit the what Maxwell's equation should be. Because what we're looking for is a network. Hopefully, one network can do all of Maxwell's equations. That would be, of course, a dream. But even for a selected subset of types of dielectric constant distributions, it would be nice to think about, is there one type of network better than another? Are convolutional networks better? Are fully connected? Do we need to put feedback loops, etc.? What we did here, we used the UNet, or are sometimes known as encoder-decoder networks, and just played around with the number of layers and the number of the skip connections, and the different, it's called hyperparameters of the network, the details of the same type of network to get the best performance. And this is the one that worked best, at least in our experiments so far. And this is what we used. So using this, and for training again for lenses, then after a large number of epochs, like 10,000, then this is for the TE and TM mode, the network roughly converges. It goes from 1 to 10 to the minus 3. This typically corresponds to about 1% error in index on the average. The training is a lot. It's 37 hours on a state-of-the-art GPU and 63 hours for the TM. There's a lot of time, and it's only 2D, X and Z. We're just starting to experiment of ways to speed things up and address the 3D problem, but I don't have any results to show you about that yet. So the training is very long, but one way to think about it, at least if you want to think of this as a valuable thing, is that you only have to do this once ever. With these Maxwell's equations and lenses, so you say for these lenses that I put in, they satisfy Maxwell's equations. They're not going to change anytime soon. So it's a very valuable network that hopefully a valuable network that you've discovered by doing this training. So this is for the what I just showed you. This is what for the spherical lens. Again, this is a lens, but notice this little bar here. It's 2 microns, so it's a very small lens. So it's a nanometer. The features are nanometers, so the sampling is typically 5-10 nanometers in the simulation in X and Z. So it's dealing with these nanostructures, which you normally could not do easily with alternative simulation tools, except for things like COMSOL. So the neural network produced this field distribution inside the lens and outside. And the ground truth, which is COMSOL, is similar. And the difference is what you see here. Again, I'm not 100% sure, or at least don't have a really good idea what is the difference. For sure, as we iterate longer and longer, this goes down. But definitely we have an edge effect of some sort. And you can see it also here, the TM difference. But anyhow, it works for a lens, and it doesn't always work. This is an example where it doesn't work. The example here is a cylinder. The cylinder is in Y. In other words, a cylinder that goes to infinity in and out of the plane of this of the display that you're looking at. The ground truth again is shows this wisp. They're called, in case you're not familiar, those are called whispering gallery modes. That you have some resonance that happens in the surface of the cylinder. Again, this is illuminated with a plane wave from the left, propagating in Z. And this propagation, some of the light gets coupled, and you can do mis-scattering for the cylinder and calculate the full field, or you can do COMSOL. In both cases, you get this well-known whispering gallery resonances. The DNN produces accurately what the field is inside, but not on the resonance, on the whispering gallery. So the residual map, the difference is just this feature. Once again, I don't have a definitive answer why that is. Maybe somebody can suggest. The best I can tell you why this happens is because the network is trained, given the index distribution, which is high here, low outside, to produce a field for all the positions at the output. So most of the values is trained, is indices around in this area produce distributions like this. And when you get to the edges, it's very different than the rest, but it's the same network that has to do it. So maybe we have to do some localization on some networks that depend on what kind of features exist or edges. So this resonance is, but most other things that don't have this. Yeah, go ahead.
So can you comment on what the ratio of the permittivities are here? Is it sensitive
class to air? Yeah.
So
the index is 1.5 and outside it's 8.
Does this become more dramatic as that ratio increases, or no?
Of course it does. If it's not, then it's if the index contrast is not that big, then just these whispering gallery modes are not as prominent, and then yeah, then it's easier. Exactly.
Mm-hmm. Okay, thank you.
But I should say that we don't really know enough about these cases where it doesn't work. The vast majority of cases that we work are like this, where we just have a contrast and the reflections are mostly backwards or elsewhere, so you don't have resonances. Okay, so what we did next, we wanted to create a database of lenses. And to do that, we took spheric lenses. So if you normally, a spherical lens means that the surface of the lens is, again in 2D, the surface of the lens is part of a cylinder in this case. Normally in 3D would be a sphere. And then these lenses can have aberrations or they need to be corrected either with multi-elements and so forth. But one way to correct it is have aspheric lenses. It's particularly for nanostructured lenses, which can be done by microfabrication. It's easier to do compared to, let's say, big lenses where you have to polish them and so forth. And this is the equation that usually it's not given by just one radius, but it has parameter k, so you can create a family of aspheric lenses. So this gives us an opportunity to create a training set of possible dielectric constant distributions to train the network to see if it generalizes. In other words, if it works for one lens and then we give it a different lens that it hasn't seen before, will it produce the right field? And fair to say that these lenses are all similar. So it's, but there also is a lot of variability. So we had a couple of thousand lenses as a training set, and then we use them to train the network that I've been describing to you. It's UNet with Maxwell as the loss function. And what you see here is two examples of lenses for the TE case, where the electric field is perpendicular. Then this is the COMSOL simulation, the field that results from the COMSOL simulation, and this is what the network produced. And subtracting the two, you get again roughly the order of 1% or less error on the average. And now that's a different lens; they can look quite different from one another. And this is the lens, and this is the field produced by the network for this. And it works both for TE and TM. That's if you're really deeply into electromagnetics, you might find this interesting. If not, probably you don't know what I'm talking about. But it's very interesting that it does the electric field quite accurately. And once again, it produces this error right along the interface, and it probably can be corrected by modifying.
Demetri, can I ask a question on the shape? These are obviously shapes that you have not used in the training, but are the parameters in the parameterization you show us, are the parameters within the range? In other words, you're doing interpolation or you're doing extrapolation in the parameter space?
Most interpolation, but also a little extrapolation. Parameter is just, it's R and K.
Right.
Parameters.
So what was the range of those parameters in the training?
I don't remember the numbers, but what you see here is the actual shapes of the surface for the parameters we used in the training set. And on the test set, there were those parameters that led to shapes either in between and also at the edges a little bit. So a little bit of extrapolation, I would say 10% of extrapolation in this shape, and the rest interpolation.
Okay. So, but the shapes that you show here are both interpolation. It's hard to tell from the shapes back to the parameters.
Oh, whether that's extrapolation or interpolation. It doesn't make much difference, by the way, in terms of the accuracy, but I don't know. I don't remember. Actually, I don't even know. I have to ask Juan, the guy that actually did the simulation.
It should make a difference. Actually,
yeah, if you go far away.
Extrapolation is already a big thing.
Yeah, I hope it will extrapolate, but it would be, I mean, hopefully extrapolate also to other aspherics that have different types of shapes. Not necessarily following this this rule.
Okay. All right. Thanks.
Okay. So why we're interested in this? Like I said earlier. Oh, by the way, because we're switching gears now a little bit, do you have any questions about how MaxwellNet works, what kind of behavior you observe, or something like was just asked?
Yeah, I actually have a question, and sorry I missed the first few slides. So what is the loss that you're using? Is it a point-wise, is it a point evaluation the way it's usually done with a pin?
The loss function is the Maxwell's equations. And then we use this field to propagate back. So the output here is a measure of the field in 2 dimensions. And we calculate the error everywhere and then back propagate it through and get
right. So you're calculating this loss using using automatic differentiation at a collection at a point cloud. Is that right?
Correct. Yeah.
Yeah, so for normal finite elements, that would be problematic, and that would be why.
Yeah, actually, that's a good question. Yeah, we use this E grid, very similar to finite FTTD, to differentiate, to calculate this the curl, we use very similar calculation that we normally do in FTDD to calculate these derivatives and then go from there. That's what you're asking.
That is what I'm asking, but usually in the Yee grid, you need this, it's tied to the control volumes underneath the Yee grid, and it's tightly, it comes from a finite volume interpretation of the finite difference scheme, right? So if you're using a neural network as some sort of like regressor for all of those point degrees of freedom, you'll lose the control volume piece of that, right? Like it's basically being reduced down to like a collocation scheme instead of, and you're losing all of this like algebraic topology structure that comes from the finite volume piece. So that, you know, the kind of thing that you were seeing, right, where when you have a big jump in the material properties and it doesn't process that, that's the exact kind of thing that you would get from doing like a collocated finite difference scheme for Maxwell instead of a Yee grid. So I'm curious, you know, I'm just sort of curious there if there's a way to set it up nicely.
Probably
preserves that.
Yeah, I mean, long time ago, many years, back at Caltech, I used to have a student that actually wrote his own FTDD, and that time I was more into it, but you probably know more about it than I do. I should say something that I didn't mention. In addition to the dielectric constant distribution of whatever the lens or whatever other element we're doing, we also put a boundary condition to eliminate any reflection. So we have this perfectly absorbing layer at the boundary, which is part of the index distribution that we give to the network, which works quite well. So we don't have to, you know, do these things of going to infinity or anything like that. So that's now this finite volume that you're mentioning. I think you mean it locally, right? To calculate the derivatives of.
Yeah, I can share some papers, and there's other things too, right? Like the involution conditions and things like that. So I'm curious, like if you were to plot the divergence of E, how that relates to the gauge conditions for Maxwell and all that kind of stuff. I mean, it's kind of remarkable how good of an answer there is without being, you know, worrying about all those kind of things that are very obnoxious to deal with for finite elements. Yeah, you know, there's stuff along those lines.
I mean, we do put a regularizer term in the network, and the network itself has some regularization just from the learning. But that's a good point. Whether the numerics, because the calculation of the loss function has similarities with you know, with the Yee grid and finite difference time domain, but and we have to calculate it throughout the volume, by the way, because this is the electric field. Here it's in 2 dimensions because all the simulations are in 2 dimensions, but normally it would be a 3-dimensional field. So 3D to 3D for from the dielectric 3D to the electric field 3D.
Mm-hmm. Thank you.
Thank you. Okay, so I'm going to move on. If you want to ask a question, please do, because like I said, we're going to go through a phase transition. And the phase transition is here. So the reason, so this is really, other than this MaxwellNet, it's not really physics kind of inspired or constrained optimization, but just an example of what MaxwellNet could do. This kind of thing, this network approach could do to help. So suppose we wanted to have a lens that would focus light somewhere here. And the current lens that we're designing instead produces a field as shown with this color map. Hold on a second, let me take, hello? Well, it's room service, so. Hold on a second, I need to take a break, I'll be right back. Yeah. Hello? Yeah, we're here on a ski vacation, so I'm up on the mountains of Switzerland, and so it's in a hotel. So somebody knocked on the door. Sorry about that. Okay, so I was saying one of the motivations for looking into this very exciting area of physics-inspired learning structures is to do inverse design, which means you have to iteratively have the structures that target candidate structures, evaluate the performance by calculating the field you could produce, and then iteratively optimize that. Again, the example here was to have a lens to focus light somewhere. And once again, these lenses that we're talking about maybe 3-4 wavelengths or 10 wavelengths most across, so it's very small structures. And then you wouldn't be able to design them with ray optics, so you would have to use wave optics. And what we're showing here, the initial lens that we would try produces a focal spot, which is this elongated yellow spot, and then other fields, whereas we would like to have a spot where the red dot is. So what we would do then, we have the MaxwellNet calculate the fields in the area where the lens is, and then between the lens and some free space, we would use just Fresnel diffraction, or just Green's function to propagate some free space and see where the light focuses. Now the question is, how do we modify the shape? And the shape is not necessarily differentiable. So what we have instead is something we call deep SDF. I'll describe it a bit. It's a little bit tricky thing to describe in a short time, so I don't expect you to fully get it, but or maybe you will. But if you don't feel bad, because it takes me a while to explain very carefully. But the idea is that you have this network that does two things. First of all, it draws the shape of the lens. So two inputs to this network are the locations X and Z in this area. So to draw the lens, you would like to have high index, 1.5 in places where the lens exists, and low 1. So if you can imagine having just these and then building a network that might draw this lens. In other words, the output would be, if you put here the two coordinates, it would be either high or low depending on whether we happen to be in a location inside the lens or outside. So this is for drawing the lens. What this is a label, a short or a compact representation of the shape of the lens, which we will use to actually will optimize over this compact representation rather than a more complicated shape of the lens sampled at 10 nanometer resolution. Even though the volume is small, maybe a few millimeters cubed, still we have much more compact representation here. So, but if we are able to do this, if we are able to build a network which has the label that identifies the shape of the lens approximately, and then the coordinates which help actually draw the lens, then we'll have two networks in a row. This network would represent the shape of the lens. This one would calculate the field. Here we would measure the field, would get an error signal, and then we could do the usual trick, come back and then modify just the latent space or the labels, the compact labels of the lenses, and find the right thing that will do the job, and that's the idea. A little more about, I won't go through this in detail, but a little more about this, just to saying it twice more or less. So again, you concatenate, or you have two inputs that are the coordinates of the output of space where you want to draw a lens, and the rest are labels, or if in neural net parlance, it's the latent space of. It's not necessarily related to the unit. It's just a representation which identifies the shape itself, the class. It's an aspheric lens with certain asphericity, whatever. And then we have a multi-layer network, which is actually, I forget now, but it's maybe 6 layers, 4 or 5 layers. And then that's being trained and to optimize to find the right representation. This is the actual cost function. This is the output of the network with parameters theta. Theta will be the weights of this network. This is the output. It would be high or low, high index, low index, depending whether the coordinates here or happen to hit inside the lens or not. And we use L1 norm, and then some regularizer to make sure that it's smooth, but that's the answer. The nice thing about this kind of optimization is that the result is forced to be 1 or 0, which if you try to fabricate the lens, if you have an optimizer that gives you a graded index, analog values, it's not clear how to fabricate this. But anyway, this becomes binary. I guess I said most of the stuff, but so I'm going to skip this. Oh, okay. So this is how we train it with a big training. So the average of this error function is about across the image, different pixels in the image, and different samples, different lenses. So once it's trained, then this network is ready to accept a latent space representation of the lens and its coordinates and draw a picture of the lens for you. And again, out of the test set, these are lenses. This was the latent space representation that corresponded to this ground truth, and this is what the network produced, and same for here. This is just to say that this idea came to us from a very nice paper that also used physics-inspired stuff in fluid mechanics. So they were using this idea to design the shape of a car by minimizing the drag and all that. And so back here, there was a sort of Navier-Stokes kind of model instead of Maxwell to translate the shape into drag minimization, or whatever they were minimizing, mapping the shape into the flow of the air around the vehicle. So that's where we borrowed this idea of how to minimize, not in the overall shape of the car in this case, or lens, or whatever else dielectric structure, but in this more compact representation like in space. Okay, so this I showed you already, but just repeating now that we talked a little bit about this. So we have a cascade of 2 networks. We try one lens, then we use this XZ input to draw the lens. So if you tell me the V and the XZ, then the network should be able to draw this picture, even though it doesn't physically draw it. Then this network fits into the MaxwellNet because this is a dielectric constant, and then the network produces the field, which then we compare to the desired output field, and then we differentiate by backpropagation and try to modify this latent space representation to find the right lens that will do the job. So this is during training. So this is what the latent space does. So it converges after a while to this, and the corresponding field gets to be much closer to the target space spot, which was here. And this is showing at the place where we want the intensity to be maximum, how this evolves with time. So again, this would be the intensity here, plotted as a function of time as the network is being trained. And then, so initially it was low because it was somewhere here. And then over time, it gets better. Again, once again, this is done without any examples of what the field should look like. It's all done based on Markov equation. That's all I have. Oh no, this is just some quantitative. This is the initial shape and the final shape, and then shows quantitatively the results. This is the initial, what it looks like a slice against at x equals 0 along Z. Then after training, we get this much more peaked value. We focus the light where we want it, and then the validation running COMSOL on this particular lens and showing that what the network found, not only the fields match, but also its performance matches quite well with what COMSOL would have produced. You can imagine having something like an optofluidic lens, some fluidic lens that changes its shape, right? Which is kind of something that I also am interested in. You have an adaptive lens that does this, so you have the network being trained and then also implemented even physically. Otherwise, you have to fabricate these lenses to do a particular task. Okay, so what's the main? I think it's the beginning. Hopefully, for me, just the beginning of a long journey, not not just a cool thing. I think it's very interesting, and of course, I've been extremely fascinated by reading the work from your group. Then, at least where we are now, the training. This is on a single GPU. It takes a long time to train, and as I said before, it may be worth doing because you can imagine making larger and larger network libraries of networks with pointers to the right thing. Because again, because we don't do this for a training set, we don't do it for, we don't find a network that will work for a particular set of input outputs. It's a network that to learn how to do Maxwell's equations. In the ultimate thing, if we do everything, any dielectric the constant distribution of a certain scale, basically you have a network that simulates Maxwell's equations, so that's done. You can only do this once, or then it can improve the performance. But anyway, for now, it takes a long time. And so for, let's say for a very dedicated problem, you have to invest in this upfront cost. And I'm not sure how much we can improve that speed. And again, it's only in 2D, not in 3D. But the readout is remarkable. It's 1,000 times faster and not even optimized. So you can read it out much faster than you could with some of these other accurate methods, and the performance seems comparable. But I guess you guys know this already. So this is the summary. Again, this is the question of generalization. I mean, so many issues to ask now. Can we start now? We've also done it for gratings. Volume gratings, small volume gratings, birefringent structures, small beads. So it works for all of those things. But we haven't been able to see some really cross-class generalization. Yeah, this was the point I talked about, the inverse design. And that's it.
Thank you, Professor Demetri.
Any questions, as they say?
Yeah, may I ask a question, please? What constraint did you have on the lens?
Adar, introduce yourself so people know how to
sorry
follow
about
up.
it. Yeah, sorry about it. So Adar, I'm from the Brown University Grant Group. I'm a relatively new postdoc here. So I wanted to ask what kind of constraints did you put on the lens itself? So the network will be in the video that you showed. It looks like it's kind of a rectangle, and only the right-hand side is changing the shape, right?
Yeah, that's a good point. In this case, we put the boundary on the left to be flat, and the way we enforce that is if you go to this representation where the XZ components are input, then you put a limit on that Z cannot be less than 0.
Okay, thank you.
You know what I'm saying? Yeah. so because here the network, this network that draws the lens, but other than that, nothing. On the boundaries up here, there is this perfectly matched layer on top, and here is the air to glass.
So basically, this the image of the lens is designed as. Sorry about that. Sorry.
I was going to say the perfect. I said something that was wrong. I wanted to correct myself. The perfectly matched layer is actually up on top here. So this is air to glass. Go ahead. Yeah.
I see. So, okay. So you have a set of rules that define this lens basically, and the network is learning those kind of dimensions or.
Yeah. So the network. I don't know why it's not playing now. Maybe I need to put it on. Yeah, so the network, learns to draw this shape.
Exactly. Okay.
And the way it learns to draw this shape is by looking at the latent space representations that it had in its training set, at that part of the network, and then being corrected to have a new latent space representation that may not have been part of the training set at all, would not normally be, but then it draws this, because it has concatenation between the coordinates x and z and latent space representation.
Got it. Thank you.
And then again, this is the same. I've shown this before.
Do we have more questions for Professor Demetri?
Demetri, for the accuracy, I think I would suggest that perhaps using adaptive activation functions. It's something that we have developed here at the group, but if you tell your student to look up at adaptive activation functions where the, let's say, I don't know if they use ReLU or hyperbolic tangent, but you can
use SelectiveAugmentation. You know what SelectiveAugmentation is? SelectiveAugmentation is like ReLU with.
Yeah, I know. Yeah. So you can parameterize them so that they not all neurons fire at the same rate and so on. So then the slope itself will determine by the data. So when you're in so that's for multi-scale problem, we have seen that, and also for this continuous problem. Actually, we're about to publish a paper on 2D shocks in aerodynamics, and we see that adaptive activation functions is very, very important.
Okay.
So that's one. Another one I would. So basically, what you're doing is sort of learning the operators. So we have something called DeepONet. Now the difference between so with it's a little different from what you're doing is basically that, but you don't only have one. You have the, of course, the autoencoder, but that could give you also. I mean, it would be interesting to actually check the results, and because we have the branch where you put the input, the trunk is the output space, which is continuous. But now, in our latest paper, we put features. Appropriate features. For example, some data is working on that now, and so you would put something like smart coordinates or some features that you expect in the, let's say, in the electromagnetic waves. If I put, instead of x comma t as coordinates, if I put x plus t or x minus t or both, then I get really, really good results.
Well, that's wonderful. By the way, just as a side thing, I mean, my motivation, or perhaps not so secret motivation for reaching out to George and the whole team is because for us, we were just getting into this and we're looking at things to do, like just like you mentioned, what else do you put in and how do you do it? And so if there's something we can do to collaborate, and maybe one of my postdocs or students can come over for a while, or vice versa. We can
sure. Especially, I mean, you made it very attractive because you said you're up in the mountains. So thanks for interrupting your après-ski to do this. But sure.
Yeah. Oh, it's a beautiful day today. It was gorgeous.
We work with, I don't know if Lulu is here, but we work with Luca Del Negro from the Photonics Center from Boston University. So we wrote early on.
Of course, I know him well. Yeah.
But you know, Luca, we wrote a paper together on Optics Express on trying to identify the two-cylinder substream from the electric field downstream. So, but we didn't follow up on that. But what we learned since then is that it's good actually to introduce a lot of features like cosines, sines, and so on into the as a basis into the trunk and to bias it. What is an inductive bias? A layer which will be inductive bias. So that's how you will enhance accuracy. And Ameya Jagdab, who's a postdoc here, he has introduced these adaptive activation functions for two reasons. One, for multi-scale problems like this. And the other one is to avoid getting stuck in a plateau. You saw, for example, there when in the first example you show us that they wouldn't converge, is basically you get stuck, the optimization scheme gets stuck into, so I assume you use Adam optimizer, right?
That was an Adam optimizer. I teach here the machine learning course. And as you know, there's myriads of problems, but what works for kind of statistical, this is not really statistical. In many cases, I think of it more as deep image prior, if you know what that is. You know what deep image prior?
No, but I can imagine, but if you can describe it.
Okay, if you take an image, let's say that's a noisy image, and you put it through an autoencoder, then it learns first to get rid of the noise.
Yeah.
Because an autoencoder is kind of, because of the convolutional layers, is more matched to natural scenes.
Yeah.
And also, this same thing is used for different things. But basically, you have only one. You don't have a training set. You have only one image, and you have the network find its best match to the image. So it can be something along those lines. Yeah, but it's just for us. I mean,
that's right. That's exactly, yeah. And we also use encoders in front of the DeepNet branch with a lot of success, for example. But yes, this inductive bias, this is what I'm talking about. Yeah, handcrafted features or automated features to induce some bias for the problem of interest.
Yeah, because we know it's electromagnetics, right? So anything, all's fair, right? You can put anything that you know that you can bias it, it's fine. The other thing that we're looking at is how you can combine now, how you can actually get data, maybe not in 3D, maybe just projections, and then try to help in this way as well, or do multi-scales, like you said, to low resolution down to finer resolution. So it's just too many things that you can think of doing next,
and also the training to cut down the time, maybe multi-fidelity computations. Not everything has to be at the highest resolution. So you can use low fidelity, high fidelity, or low resolution, high resolution, or simpler models, higher models. So we do that a lot actually. So we have a few papers on multi-fidelity training.
Yeah, because the computational cost is really computing this, the E grid, computing the derivatives of the electric field. So actually, let me introduce Carlo. Are you there? Carlo?
Yes, sure. Yeah.
So Carlo,
nice to meet you.
Ideal. Carlo Gili, he's working with me on this. The student that did his PhD on this, he moved on. He works at Microsoft now in Cambridge, doing very exotic stuff. But so he doesn't even answer my emails anymore. No, he does, but with a big delay. But Carlo works with me on a daily basis on this. So if we were to pull some thread out of this, would be Carlo working with somebody on your end. So that's why I thought I would introduce him.
Yes, something concrete like a comparison with DeepNet would be interesting at this point, and then maybe we can throw some features, like we said, and see how we can enhance accuracy, reduce the costs. We all have the same problems.
Yeah, I mean, I must say that I haven't been able to follow all your work, but I think it's remarkable. Yeah, that you guys were way ahead of time. There's something else that we also call learning tomography. I don't know if you've seen that. I thought of including it today, but I thought it would be too much. I can tell you some other time. But there we use a physical model of propagation, but constructed like a neural network. And then we use error back propagation and everything else to identify. In that case, we go from field to index of refraction. Yeah, this is the opposite from index to field. So there, the structure of the network itself is based on beam propagation, BPM.
Nat, do you want to introduce yourself not Trust from San Diego. He earlier he I don't know if you guys want to exchange any information, but
Sure, yeah. I'm at San Diego National Lab. I have a few projects doing structure preserving machine learning. So for things like electromagnetism, and other things where you need more sophisticated discretizations, that's kind of the focus of my group there. So I actually track, and we're working on the same problem for Maxwell. When you have jumps in material properties, how do you reliably get it to work? I found is your email the one on your, is this the best place to get a hold of you, Demetri Psaltis at EPFL?
Yeah, that's me.
Hey,
Nobody
okay.
else calls Demetri Psaltis at the BFL.
Yeah, I'll follow up. I'll send you an email, and I can share some of the papers we've written in this direction.
Fantastic. Yeah. So, like I said, I actually, if you have another question, I'll take it. But in a few minutes, I need to go. But I do hope that we'll find something to do together. Primarily because of being selfish. Because I feel we can waste a lot of time, barking up the wrong trees. So, with your experience, maybe you can find something to do that's more shortcut.
Hey, can I ask a question though? Have you looked at so this was all frequency domain. Have you looked at like time? Do you have any interest in time domain? Are you working in that direction now?
Very much so. I'll tell you why. Because we have a lot of interest in doing nonlinear optics calculations. And of course, it's possible to do with other tools, but it becomes more difficult. Whereas here, just Maxwell's equation, you just add the extra term, the quadratic term, or whatever it is in the loss function, and you can do these simulations. But in practice, the nonlinear optics happens with femtosecond pulses or short pulses. So yeah, Carlo is working exactly on this, for example.
Yeah, there are many things that we would like to try. For example, here there are many parameters which are fixed. For example, the wavelength, the incident direction, and many things that we would like to explore and see if we can introduce other parameters into it, and still if the model can generalize. By the way, just a further detail, which comes back to the previous question. In this case, which is a bit different maybe from the PINN you are used to, our grid in this case is fixed. The X Z grid, I mean, is fixed. We are not giving, let's say, the point to the network. I don't know if this should release a bit the constraint about the volume size we were discussing before. Basically, in our case, we not changing the volumes. I don't know if this should some way make the FDDD computation, let's say, more robust.
You have points on a lattice, right?
Yeah, we have point on a lattice on a grid which is fixed.
Yeah. DeepNet, you can work on a lattice, like what they call the FNO at Ecole, but you don't have to work on a lattice. You can work on any arbitrary. In fact, it's so that.
Yeah, for that I was saying, because I'm reading those papers. Yeah, this.
Well, thank you very much, Demetri. Thanks, and you can continue your press key, and we will continue here with another talk.
Very good. Thank you for having me. And like I said, I hope there is something next. But we have to. If you can send me some things that you think are relevant, then maybe we can reply to that.
Okay. Take care.
Bye-bye.
Bye.
Professor Demetri.
Yeah.
So we move ahead with our next talk. Our next talk is from a member of the Crunch group, Zongren. Zongren, yeah. So he would be presenting to us a paper review on improving out of distribution robustness via selective augmentation. We all know him, but a little bit about him. He's a third-year PhD candidate and my co-host at Crunch seminars. And yeah, you may want to share your screen and go ahead with the seminar.
Right, thank you. Today we're going to study a paper together on this improving out-of-distribution robustness via selective augmentation. So the main reason we're interested in this paper in the first place is that one of the authors of the paper, Feng, she is also one of the authors of the model agnostic popular model agnostic meta learning paper. And for this one, instead of the general meta learning method, we like she and her colleagues were more interested in domain generalization. So, and the target of this, this paper proposes method. And the target of the method is to improve the output distribution robustness by way of data or training augmentation. So the problem with this method, so we can all think about this during this talk, that the problem is this method is not easily extended to regression problem. It's just for classification problem, but you guys may think about how there any way to extend it to the regression problem easily. And the first question is, what is the out of distribution problem? What is the OOD? The paper categorized the out of distribution into two types. The first one is the subpopulation shift, and the second one is domain shift. For subpopulation shift, is that the test set has the same support as the training set, but it has different distribution. Like for example, this unbalanced data in training stage, but balanced data in testing stage is one subpopulation shift for this out of distribution. So we have there's no unseen sample in the testing stage, but the distribution is different. Like for this example, during the training, the training data is unbalanced, so which may cause some trouble in the inference testing stage. The second type of this OOD out of distribution is domain shift. That is, the test set has different supports. So there is some new data which is unseen in the training set, but we have to make prediction or inference on those unseen data in the test stage. So those two, the subpopulation OOD may result in learning the wrong feature output relationship, while the domain shift may result in bad generalization. So from one domain, the same domain in the training set to unseen domain in the testing stage. And here are some notations that will help us understand this method. So this D, capital D, is denotes the domain. So we have a total capital D domains, data domains. So instead X is the input, Y is the output. Instead of X, Y pair for the sample, we have additional auxiliary variables D, which denotes the which domain this sample comes from. So like for this domain, for this small D domain, we have in total capital N to the D number of samples. And data distribution is for this one is actually a mixture of domains by some mixture probabilities. So here this probability distribution for the training set, and this is the testing set. So and this R sub D of training and R sub D of testing are the mixture probabilities. So for training set, the domains are actually the set of domain whose mixture probabilities is non-negative. No, sorry, is greater than 0. So for those domain whose mixture probabilities are 0, then like those domains are unseen in this distribution. So for the first type of the OOD, the subpopulation shift, like those D training and D testing are the same, but they have different mixture probabilities. That's how we call this different distribution. And for the second type of OOD, the domain shape, the distribution of the data are different. For some case, for some D, this mixture probability in the training set is 0, but for this D, this mixture probability for the testing distribution is non-zero. That's another type of the OOD. So before I go to the method proposed by this paper, I want to spend some time on this mix-up strategy, which is like the paper is this selective augmentation for improving the output distribution is based on this mix-up strategy. So this is a popular popular strategy for improving performance of neural network. And the basic idea is very simple. That during the training, during every iteration of the gradient descent, we sample one, like we assume that the batch size. We're using the mini batch stochastic gradient descent, and the batch size is just 1. So for each iteration, we sample one sample from the data, from the training set, xi, yi, and we use this pair of data, this sample to compute the loss, and then we compute the gradient, and then we do stochastic. We do gradient descent. So instead of just sample one data from the training set, this mix-up strategy samples two randomly from the same training data distribution, and then for this two samples, sample I and sample J, they do this very simple interpolation. So it's kind of a linear convex interpolation where this lambda is greater 0 and smaller than 1. And then this lambda is also randomly generated. So for each pair of sample I and sample J, they do this linear interpolation to obtain a new sample x tilde and y tilde, and they use this strategy uses x tilde and y tilde to compute the loss, to take the gradients, to do gradient descent. So this is really simple idea, yet very useful. So a lot of people prove that, not prove that, empirically prove that, show that it has many advantages. It has better performance in accuracy for some cases. It increases this mix-up strategy, increases robustness when learning from corrupted labels or adverse areas examples, and improves generalization for some cases. And it also stabilizes the training of GAN. So this strategy, mix-up strategy, is really simple, just easy to implement, easy to understand, but very useful for deploying neural network problems. And this makes, for those who are familiar with one paper of our group, the physics-informed generative adversarial network, PI-GAN, this mix-up strategy is actually used in this paper to stabilize the training of the GAN. And I quote here, so this is, we don't have to be, we don't have to talk about it again, but here for the training of the discriminator, the loss of discriminator, here the X hat is actually an interpolation between a fake data and a real data. In the same way, for the mixed up strategy. So, and in this way, the training of GAN, like I didn't test it, but a few members of our group did tested this strategy. It stabilized the training of GAN, so which is quite useful for other people. However, the paper, not the mixed up strategy paper, not the physics informed GAN paper, the original paper for the improving the auto distribution performance claim that this mixed up strategy does not improve the OOD robustness, which is understandable because the mixed up strategy interpolates samples from the same distribution, from the same domain. So it improves the training, but it doesn't improve the robustness, the domain generalization or the auto distribution robustness. So instead, the paper, this is the main part of the paper proposes a method for improving the auto distribution robustness. They call it LISA. So learning invariant predictors with selective augmentation. So here's the selective augmentation. I consider it as one data augmentation strategy. So this select samples with some criteria to enhance, to improve the robustness through. And then the predictor after training is completed, this predictor should be domain invariant. That is how the auto distribution robustness is improved. So they have two strategies. So the one is interpolating samples with the same label, which means that we sample from different domains, but with the same labels. So in this way, the training, the machine, the neural network is enforced such that, you know, the feature that result in the same should not be related to the domain. In this way, like the features or the predictor is domain invariant. And the second strategy is interpolating samples with the same domain, but with different labels. So it tells the machine that even from the same domain, the predictor, the labels could be different, such that, you know, the predictor is enforced to be invariant to or unrelated to the domain, because like for the same domain, different type of labels. So this is a whole training procedure of LISA. From this lambda is also from 0 to 1. It's a randomly generated number for each iteration. And for each iteration, it's the method samples, as always, sample set of samples B1 from the training data is a batch size. No, it's a batch of you know, from the training set. And for this B1, is randomly select strategy 1 or strategy 2 with some probability prefixed probability. It could be 0.5 and could be 0 if we only want to 0, 1 if we only want to use one strategy. So for each sample of B1, it uses one of the strategy to sample to construct a different method. A different sample, either a sample from the same domains with different labels, or sample from different domain but with the same label. And after it's this another batch B2 constructed, it uses this mix-up strategy such that we can do an interpolation between samples in B1 and samples in B2 respectively, and the method LISA uses this one to compute the loss and finally compute the gradient and do the update. So this method is also very simple compared to the mix-up strategy. So easy to implement and easy to understand. So here are some. I don't show their results, but I want, you know, this method has some problem, and for us, for the scientific computing guys. So here are some comments. So this method is actually a generalized balancing strategy. It kind of so for regular balance strategy, we balance among data. We don't want to see unbalanced data during the training. But here, not only it balances the data, it also balances the labels and domains. So in this way, the domains generalization, the auto distribution generation is incorporated. And second is it is interpolation rather than extrapolation. That is the nature of mixed-up strategy. And third one, I think is most important for all of us, or at least some of us. I don't think it can be extended to regression problem. Like I raise a very simple example. So the target is we want to learn a derivative operation on sound waves. So those sound waves are parameterized only by its frequency. We want to learn the derivative operation by MaxwellNet. So the training set or training distribution, we have, so this is a mapping. We want to map sine omega s to omega cosine omega s. It's this derivative take a derivative. So this omega s, I'm sorry, this omega are sampled from a mixture of uniform distribution. So here one have, I mean, there's so it's a hierarchical probability distribution that we first decide which domain we go to, and then we sample omega from this domain. Like here, the mixture probability are equal to be 0.5. And then the test side, the test distribution, still we want to predict derivative of the input sign, but this domain is unseen from the training. So the domain is actually a linear interpolation of uniform from 4, 6 to 6. It's actually a linearly interpolated by those two uniform distribution. But since we're deep net, we're learning operation on the function space. So non-function space is no longer simple linear interpolation. So for this simple task, this domain generalization problem, I don't think it's possible to use this Lisa strategy to improve the auto distribution robustness. If we don't apply any techniques to improve the domain generation, then the prediction, we're training on this and we testing on that, the result would be not good at all. So, and then this, I don't know if the audience has any idea how this Lisa method could be related to the regression problem. I don't think so. So it's a pretty, bad news for us. So I don't, and then this is probably one reason why it was rejected by ICR 2022, but of course it's not the main reason, but okay. So domain generalization is actually an active research area. People are interested in how we do this auto distribution or domain generation in machine learning. So this is I'm not going to talk about this survey paper.
Can I ask a quick question? This is
yes,
John.
Yeah.
In your previous slide on the DeepNet example,
yeah,
I think under certain condition, this can be possible. For example, if in the middle domain, like 4 to 6, the function you wish to approximate can be approximated by the function you get on other 2 domains. I think that can be possible.
You mean like a linear combination of functions from those two domains, something like that?
Yes, but not just a linear, but you need to apply some other nonlinear transformation, like applying neural network stuff, so that I think your trained set sufficiently expressive enough to represent your task distribution in this regression task.
Yeah, but so, how do we, like for Lisa?
So I'm trying to say that Lisa doesn't work because they're just a simple this convex combination that's just a linear. So I think this approach wouldn't work. But like in the step 9, you have just a linear combination, right?
Yeah, you mean here we do a nonlinear combination,
right? So you need to have a. I think this is some task specific, so that you need to learn that transformation, so that the data has to be phi of sub B1 and B2, and those data should represent the out of distribution value. So I think those, okay. My comment is linear relation wouldn't work, but non-linear there might be.
Yeah, but that would be very good, like suggestion for how we.
I think you might try assuming you have underlying oracle, so that B1, and you may, I think, go back to your example on DeepNet, and I think I let me think about this later on. Let me give you an oracle. Then you may test it out, see how far you can approximate on the out of distribution if you have an oracle. I think that might somehow justify how far you can go in this task. That
right. I agree with Shind. I think this can be done actually. This specific example can be done just like what Young John is talking about. So don't dismiss it so early.
But there's another thing about this one is how do we select B1? How do we select a B2 corresponding to B1? Because the strategy of Lisa uses labels. So example from the same domain but different labels. The example from the different domain but with the same labels. But for regression problem, we don't have labels. So the problem with SEP9, yes, we could solve that with nonlinear instead of the linear convex interpolation. We can use a nonlinear operator on those B1, B2 samples. But how do we fix those two strategies?
You're right. So
right. So we can think about it.
Underlying message is Lisa doesn't work. We need to develop a new one that works for this task. I think that's the take-home message. I think.
Okay. So the reason why I want to mention this, I don't want to talk about this paper. I want to mention it because there's one specific technique for domain generation. Like Lisa does not work for regression problem easily. So maybe there I think there exists other methods that work with regression problem instead of just like Lisa samples, constructing samples based on labels. So there's one paper from I found it from the previous survey, a meta learning for domain generation. So this method, this paper is actually very interesting in a way that it is very similar to the original like Finn's model agnostic meta learning method. So if I think 1 year ago or 2 years ago, I was the one who introduced this MML to the in the Crunch seminar. So I don't know if anyone still remembers that, but this is another way to do this domain generation. Instead, like we don't do selective augmentation, we don't do data augmentation, we do meta learning among the domain. So it's very similar to the original model agnostic meta learning, one of the most popular meta learning methods. And here, MML, like for meta learning, we have a meta training stage, we have meta test stage, and the final one, we have meta augmentation stage. So MML actually, original MML minimize the meta test loss. Test loss is, is computed after the step 6 and step 7, and this method, this meta learning domain generation MLDG, actually minimize the meta test loss and the meta train loss at the same time. So in this way, MML actually learns to learn fast. So it doesn't learn to learn accurately, it learns to learn fast. After the training is completed for MML, we actually need to do fine tuning for the neural network to learn accurate for new tasks, new unseen tasks. But for this one, this meta learning domain generation MLDG, because it minimizes the meta test loss and meta train loss at the same time, this method actually balances between fast learning and accurate learning. So after the training is complete, we don't need to do this fine tuning. We do, we directly use it to do inference for and unseen domain for different types of distribution problems. So I think that for regression problem, if we are interested in domain generation, this is a better method to consider than the Lisa. But still, like Jim suggested, we can find a way to apply Lisa for regression problem. And that's it. Yeah, this is for this. It's a short paper. It's an easy one, and unfortunately, it cannot be extended regression problem easily. So we can talk about that later. So
Zongren,
any
can
questions?
you have the paper? You didn't show us any results from the paper. Can you show us one? Can you show us the paper and show one result?
Let me check. So there are many. Their results are showing in the table. There are many similar domain generation or this auto distribution methods. So they show that their Lisa is a kind of beat everyone for the same. But not all the cases, but for some cases. So it's not easy to plot the results because this is not for like for instance, this is one example they consider the amnist, the colored amnist. So this is not results. How they show this mix-up strategy work. Like for they categorize it 0, 1, 2, 3, 4 into one category, and 5, 6, 7, 8, 9 to the other one. So they are showing that from the same, with the same label, like from digits larger or equal to 5, or same domains but different, with the same label but different domains. Their color are different. For the bottom is that they have the same domain, but with different labels. So I don't know, George, what do you want for results? So they don't give figures for those results. It's just tested. That's why I didn't put any result because their examples are the classification examples. We're not really interested in that.
Well, we're interested in classification too. There's lots of biomedical modeling we do with its classification.
All right, my bad. Yeah, in this way we can use this Lisa strategy.
Yishan used a mix-up in her thesis for the diabetes problem. She used mix-up, and I think.
What is her goal for mix-up?
Well, she was doing a classification, but also I think, and Rui, right? And Rui, you also use mix-up for the genotype to phenotype.
Yes, yes.
So don't dismiss so easily. Chelsea Finn is a smart person.
Yeah, I know.
Just because the
I'm not saying their paper is bad. I'm saying it's not easy to use their ideas for
some data. What do you think of the second of these MD? What's called MLDG?
This one?
Yeah. Yes. MLDG. Some data. Have you looked at that, Domna? Because some data is working on domain adaptation.
George, the primary part which he began saying that the difference in distribution and that is what in other papers they refer as the covariate shift and the distribution shift. So I'm not sure if I've not looked into this paper. I'm not quite sure if this method will work for the problems that I'm trying.
Well, because like Zongren said, I think it's the MAML is fast because you do everything, but it's not so accurate. We beat it with the functional priors easily. Here with the it's more costly because you also minimize those losses at the same time. So probably the optimizer is low. But if you can gain robustness and you get generalization, that's all we are looking for. That's something I want to maybe for the shape optimizations that we're doing with Varun, or we're trying to do anyway. If you can look at it, this will be something interesting for the geometries, like the previous speaker was also talking about.
Yeah, sure. I can take a look at that, Professor.
Yeah, that looks to me simple and actually makes sense.
Yeah, I think this one is a better choice if we want to start domain generalization. It's very similar to MML. I like it. And then also minimize it. Try to learn accurate instead of just learn fast.
The other question on Zongren I have is, you know how Shuhui took the MAML and generalized it to functional priors, right?
I think he compared
Yeah.
with
But
MML,
if you think about it, what the MAML does is it gives you the average of all the tasks.
Yes.
And Shuhui gets a distribution, right?
Yeah.
So in some sense, it takes the one line and spreads it into, so it has a whole distribution, is more informative. So you don't throw away all that information that the ML does. I wonder if we could think of how to actually create a distribution version of the MLDG in the same spirit, not just just the average.
Oh, you mean
of the network?
Like domain prior, something like that?
Yeah, exactly. Like
okay, I can think about it.
Yeah, exactly. Remember what the previous speaker talked about, the image prior?
Yeah, I know that. I know image prior.
Yeah.
Right.
Domain prior, yeah.
Domain prior. But image prior is not, they're actually not the same. Image prior actually, it learns an autoencoder from the noise to the.
No, I know.
Image, corrupted. Oh, yeah.
Right. I'm talking about taking MLDG and make it functionalize it like we did with distribution, like we did with the functional prior. Some data is working on this. That was sort of a pet project that she has. So I'm interested in somebody picking up. Maybe we can have Arun or somebody, but this is a big deal, right? Obviously, in any design problem, we'll have to encounter that.
The best one till now I felt was the transfer learning method, which with the multiple basis function that was proposed by I forgot his name, but we had the Scrum seminar from him who had
Harvard, Matthiakis, yeah.
Yes. I'm trying to compare my method with that. So till now, that is the best one that I have.
All right, we can discuss about that later this afternoon.
Okay.
Anyone else has experience with domain generalization, the domain adaptation?
Those two are different. Domain adaptation and domain generalization. Yeah, there's a little bit different from
Hi, George. This is Panos. Panos Tinis from PNNL. So I would like to make a comment for this mix-up that you presented before. I've always found it peculiar that it's working. And I think that what Yeonjong said, there is something in there that instead of a linear combination, I was thinking that maybe some ideas from information geometry could help, which considers that you have different distributions, that you cannot just take linear combinations because they live on a manifold. So there has to be something better to do with a nonlinear transformation that will combine the different distributions. Because I always find it strange that the mix-up, which just takes linear combination of things, works. There has to be a better approximation.
Actually, I don't know if you remember the work by Greg Valiant, our collaborator. Right. He doesn't make the claim now that it works as improves the accuracy, but actually as a regularizer.
I see. Okay.
So he has shown results on that.
Yes. I see. So
the robustness is true, but not necessarily
the accuracy.
Improving the accuracy.
I see. That I understand. Yes, because you can increase robustness by doing things like that. I understand. Yes. But if you want to increase the accuracy, I find it very almost simplistic to just take linear combinations of two different distributions, right?
Right. So, and for some cases, I think it will fail. Like for a concave distribution, a linear convex combination interpolation will go outside of the domain if the domain is concave. So it's not always the case.
Exactly. And that's why you need a different combination, right? That takes into account this curvature there. And that's
Yeah,
what
geometry.
information, that's what information geometry does basically. It takes information not just from the linear, the tangent, but goes for the curvature, which is a second order information.
Yeah,
Yeah.
right.
Yeah, George, you remember the work also that Charbel did many years ago, where they were trying to do uncertainty quantification and trying to get points which are between the known points that they had in parameter space?
Kind of, yeah.
Yeah, but that was almost 10 years ago. I mean, where they were trying to get this, they assumed that these parameters, they cannot just take linear combinations of parameters, but you had to do something more sophisticated.
Oh, so for the manifold, right?
The manifold, yes,
And
yes.
projection, yeah.
Yeah. So I was thinking that, here maybe something like that could give you better accuracy. But as far as robustness, I agree completely that it's probably more robust to do it this way.
Okay.
Yeah. Okay. Thank you.
Zongren, there's one paper on deep transfer learning by conditional shift. So I guess that is something we could try. I'm trying that with Katyana, but I think that's giving me promising results, at least for some PDs, but I haven't tried them for complicated PDs. But yes, they are giving some promising results till now.
Mm-hmm.
It's using conditional shift.
Could you say the title of the paper?
It is, just give me a moment. It is Deep Transfer Learning for Conditional Shift in Regression. It's by Zhu Liu.
Put it on the
Yeah, I'll put it on the chat.
Okay, thank you. I'll take a look at it. Okay, we can discuss later about this one.
Okay, some data. Maybe you can close this and.
So thank you, everyone. We are closing a little early today, and wish you all a very happy weekend. Be safe.
Bye.
Bye.
Thank you.